singular matrix. Here I already said that the rank of this matrix is 2. Yeah? So assume you have a squared matrix, A, n rows, n columns. When is it full rank? Well, it's full rank if the rank of A equals n. Here, if the rank of A would equal 3, it would be full rank. In this case, it is not. If A is not full rank, yeah, we call A a singular matrix, and a singular matrix does not have an inverse, and the determinant of a singular matrix is 0. So this is very important to understand that what singular matrices are. Yeah? Singular matrix has a determinant equal to 0, has no inverse, and is not full rank. Okay, let's go on this side. Here we define the identity matrix. It's denoted by I, and basically it has ones on the diagonal here and zeros everywhere else. The characteristic is that A times I equals I times A equals A. Be careful here. This we call the commutative characteristic. Normally, in a matrix, A times B is not the same as B times A. Yeah? It's only true when you have the identity matrix. Now the inverse of the matrix, we denote that by A minus 1. The definition is if you do A minus 1 times A, you should have the identity matrix. This is only for squared matrices. And keep in mind that not all square matrices have an inverse. We just see here, if your matrix is singular, you do not have an inverse. Alright, final set of characteristics. These are two that are important to know. Once we're in the course and we encounter these, I will remember that we've seen it. If you do a transpose or an inverse of a product of matrices, you swap the matrices, right? So AB transpose is B transpose times A transpose. And the same for the inverse, so don't forget to swap. Pseudo-inverse of a matrix is something we will use, for example, when A is not a squared matrix. When A is not a squared matrix, A does not have an inverse. And if you have a matrix working on a vector and you solve for x, then this A transpose A, between brackets A transpose, is the pseudo-inverse. No need to remember all this. When we encounter this, I will let you know and remembering the linear algebra refresher, we discussed this. Also here, eigenvectors, eigenvalues. We've seen that you have a two-dimensional grid of unit vectors, and we apply a matrix to that vector. Then we see that what we get as a result is rotation and some scaling. Yeah, so this vector became longer, and that's typically the case. Whenever you multiply, whenever you have a matrix working on a vector, you will see these. Now, the vectors that are unaffected by the transformation, these vectors are called eigenvectors. And the magnitude of the eigenvectors are called the eigenvalues. Intuitively, where could we see this? Well, sorry, here I made a mistake. Yeah. This could be a pixel. Yeah. And we have a matrix A transforming this one to this one. You can clearly see that nothing has changed on the x side. So the pixel vector x is an eigenvector, whereas you see it's clearly not the case in y. So whenever this is a picture, imagine this as a picture, you see it a bit distorted. Yeah. Okay, now just for fun, the formula is AV equals lambda V. This means that a matrix working on a vector is just a scalar times the vector. Yeah? So we can change this and say that AV minus lambda, and I add the identity matrix here, V equals 0. Yeah? So I can put V outside of the brackets, and then I have A minus lambda times the unit vector equals 0. Now V per definition, an eigenvector is not 0. Yeah, that's per definition. So that means that this term must be 0. Yeah? So this cannot have an inverse. You cannot have an inverse of 0. So cannot have inverse. Not inverse, this means, as we've seen, this is called a singular matrix. Singular matrix. And that means that the determinant equals 0. Yeah? So A minus lambda, the identity matrix, equals 0. We call it characteristic equation. Just for your information, no need to remember, but remember that eigenvectors are vectors that are unaffected by a matrix transformation. Okay, now this was it for matrices. Now we'll take a look at tensors.